All right, so here we have an object of 1 kilogram. It's initially moving rightward at a speed of 2 meters per second along the x-axis. Is acted upon by a force f of x that varies with precision as shown in the graph below. So part A wants us to find the instantaneous speed at 2 meters. Part B wants us to find the KE at 6 meters. And then C wants us to find how much work is done between 2 to 10 meters. And then D wants us to find the instantaneous speed at 12 meters, which is pretty much the end of the graph. All right, so then that here we have an f versus x graph. It says that the f is constant for a little bit, and then f varies a little bit, and then it stays constant again in the negative direction. All right, other than that, let's crack it up. Okay, so here in part A, it wants us to find what is the instantaneous speed at 2 meters. I think the easiest way to do is just to use the work-kinetic engine theorem. Well, here we know net work is the change in KE, which can be broken down into KF minus KEI. Well, it wants us to find the instantaneous speed at 2 meters, which implies that it wants us to find VF. Okay. All right. Other than that, I'm going to solve for KEF. Why? Because VF is hidden in KEF. So to get rid of negative KEI, I want to move negative KEI to the left side of the function, which changes sign. So it goes from negative to positive. Here I have net work plus KEI, which is equal to KF. Here I can go ahead and break it down into 1/2 mvi squared for KI. Net work I can find by using the area of the graph in just a second here. And in KF, I can break it down into 1/2 mvf squared. Why? Because I need to find what VF is at 2 meters. Well, because the problem just wants us to find that, or the instantaneous speed at 2 meters, I'm just going to go ahead and shade only the area that pertains to part A. Okay. So because part A only asks us to find the speed at 2 meters, I'm just going to shade in the area underneath this f of x graph for just 2 meters. Well, here to find the area, this one's pretty easy. The base is 2, the height is 20, so 2 times 20 is 40. The area beneath an f of x graph tells you the work done on the system. So here, keep that in mind. So the work done on the system for the first 2 meters is 40 joules. So here, net work is going to equal to 40, and then I have everything else, okay? So net work, I'm going to replace it with 40 joules. 1/2 gets carried down. Mass is 1 kilogram, as given in the problem at the very top in the black here. And then the initial speed is given as 2 meters per second. So I'm just going to put that. Don't forget to square that. And then on the right side, 1/2 gets carried down. Mass is 1 kilogram, and then VF is our only unknown, or VF square is only is the only unknown. All right, on that, I'm just going to simplify the left side. Here, 1/2 times 1 is just 1/2. 1/2 times 4, because 2 squared is 4. 4 times 1 is 4. 4 times a half is 2. 2 plus 40 is 42. That's where that 42 comes from. And then last but not least, on the right side, I'm just going to leave it the same. But if you think about it, 1/2 times 1 is just 1/2. Okay. So here's what I want to do. In order to get VF squared by itself, I'm just going to multiply both sides by 2. So 42 times 2 is 84. So I want to say that VF squared is equal to 84. Therefore, to find VF, I just need to square root both sides to get rid of the exponent 2 here on the right side. So therefore, VF is the square root of 84. And the square root of 84 is going to give you about 9.17. That is this answer, or that is the speed at 2 meters, which is the answer to part A. I am done with part A. However, if you wanted to, you can totally use kinematics, okay? When you're given these force versus x graph, you just have to realize when f is a constant. So for the first 2 meters here, I realized that f is a constant 20 newtons because it's just a horizontal line, right? It hasn't varied yet. So I can use kinematics equations here. What I made a statement here, I can only use this because f is a constant. If f is a constant, it implies a is a constant. If a is a constant, you can use your kinematics equation. So here, in order to get VF, I want to move negative VI squared to the right side. So therefore, I can say that VF squared is equal to 2a delta x plus VI squared. And I know everything almost. Well, I guess I know almost everything. Here, 2 is carried down. A, I highlight because that's unknown. But really, you can find it pretty quick. Delta x here is 2 because it sets the first 2 meters. And then VI is 2 because the initial speed is given as 2. And then, again, square that. So here, to find A, I can set up Newton's second law, net force equals ma. To solve for A, divide both sides by m, so F over m is A. Here, F is 20 newtons. I want to redirect you to the graph here. Over here, for the first 2 meters, the force is a constant 20 newtons. Well, F is 20 in the numerator. Mass is 1 kilogram, so 20 divided by 1. will give you an acceleration in 20 meters per second squared. Now that I know A, I can plug it back into A that's highlighted in yellow here. So therefore, I'm just going to carry this function down. VF squared equals 2. Carry down. A is substitute out for 20. And then 2 meters per, 2 meters here, which is the distance that's being applied for. And then, what is this? 2 squared gets carried down. Alright. So, what is this? 2 times 2 is 4. 4 times 20 is 80. And then 2 squared is 4. So 80 plus 4 is 84. And that's VF squared. So to get VF by itself, square root both sides. So therefore, the square root of 84 is also 9.17. Once again, it is the same answer as I got using the work-kinetic energy theorem. So it's up to you if you want to use kinematics when F is a constant, or just use the work-kinetic energy theorem. All right, let's crack out part B. Okay, part B asks us to find what is the kinetic energy at 6. So here, I've already gone to 2 meters. It wants it at 6 meters, which is right here where my cursor is circling back and forth. This is pretty easy. Once again, excuse me. I want to apply the work-kinetic energy theorem again. Why? Because the area underneath an fx graph is the net work done. So why not use this particular function? All right. So therefore, I want to break delta k e into kf minus ki. Here, it wants us to find ke at 6 meters. That suggests that I need to find kef. Okay. All right. Other than that, I'm just going to move negative ki to the left side, which makes it a positive value. Net work here plus ki equals to kef. Well, to find net work for the first 6 meters, I already know the first 2 meters is 40 joules. Well, it wants it now all the way to 6, so I'm just going to add this area that's shaded in blue here. So therefore, to find this area, this is a right triangle. I can just apply a 1/2 times base times height. Here, the base is only 4. Please count carefully. From 2 to 6 is a difference of 4. Well, the height is 20. So 1/2 times 4, which is 2. 2 times 20, which is 40. So this area is also 40 joules. So therefore, 40 plus 40 is 80. So therefore, the net work done for the first 6 meters is 80. All right, and then KI, I already can just calculate this. KI is just 1/2 mv squared, and then 1/2 times 1, which is 1/2. And then V is 2. 2 squared is 4. So 1/2 times 4, which is 2. Or you can just rewind the video, and that was calculated in the previous part. All right, other than that, 80 plus 2 is 82. So the answer for that is 82 joules. All right, let's go ahead and crack out part C. Part C wants us to find how much work is done by this force as the object moves from 2 to 10. Well, it's specified from 2 to 10. So make sure you understand the graph and you're assessing the interval that it asks carefully. It says from 2 to 10, not 0 to 10. All right, so on that, I'm just going to find the net work by just really measuring the area, okay? But it says from 2 to 10 though, so in my animation here, I'm just going to go ahead and take out the first 2 meters. Why? Because it says from 2 to 10. So I don't need that first 2 meters, okay? So make sure you shade the proper area. I'm going to keep from 2 to 6 because I need to go from 2 to 10. Well, here, this area that is also a right triangle. Once again, the area of a right triangle can be calculated using 1/2 times base times height. This area here is 1/2 times the base being 2, because from 6 to 8 is 2, and then you go all the way down to -10, and that is an area of -10. Well, here, the shaded area in the purple here, the base is 2. This is a rectangle. From 8 to 10 is 2, and you go all the way down, so 2 times -10 is -20, okay? The work beneath the x-axis is negative because it's work done against you. All right, on that, I'm just going to go ahead and count up the shaded area. Here, this is a positive 40. This is a -10. That's a -20. So 40 minus 30 will give me an area of 10 joules. So the net work done is a positive 10 joules. All right, and that is the answer for part C. Now let's go and crack out part D. Part D wants us to find the instantaneous speed at 12 meters. So really the whole entire graph. I'm actually going to go ahead and start from 0 and go to 12 because I already have a lot of information here. To find the speed at 12, which is VF again, I'm just going to go ahead and break up net working to delta KE, but delta KE is KF minus KI. I want to move the negative KI to the left side, which adds it just like over here. Net work is equal to KF minus KI, but if I solve for KF, I need to get rid of this negative KI which I'm going to move to the left side. So it looks like this statement here and the third line in blue, okay? So essentially, I'm doing the same thing. I'm just going to carry it down here. All right, other than that, I know the net work done. So here, I want to put the green shaded area back. Why? Because now I'm just going to start at 0 and go all the way to 12. So I already know that was 40 joules, and the only area I need to shade in is from 10 to 12. Well, from 10 to 12, it's also negative 20 due to symmetry. So if this area here is 20, this area here is also 20. It's negative because it's beneath the x-axis, so therefore that's also negative 20. All right, other than that, if you count the areas correctly, 40 plus 40 is 80, minus 10, that's 70, 70 minus 20, that's 50, and then 50 minus 20, that's 30. So the net work done here is a positive 30. The KEI, once again, is calculated previously, and the other parts is 2 joules. Other than that, I want to break KEF into 1/2 mvf squared. So as you can see, the left side, 30 plus 2 is just 32, and then 32 times 2 is 64, and that's VF squared. And then to get VF squared by itself, square root both sides. So therefore, the square root of 64 is simply 8 meters per second. And because they asked for average speed, I am done there. I don't need to specify a direction. All right, I hope that helps. Stay needed, don't be whacked. Okay. Oh, by the way, I was gonna say, if you wanted to, for part D, right? I started from 0 to 12. If you wanted to, hold on, I got you. I delete all this because I could actually start from 6 meters, because in part B, it asks us for the kinetic energy at 6 meters, which is right here, where I'm circling back and forth. So I can just go from 6 to 12. If you do that, you can just apply this, right? If you look from 6 to 12, right, if you watch my cursor, if you look from 6 to 12, if I count all the areas underneath it, it's negative 50 because it's negative 10, negative 20, negative 20. So that's total negative 50. That's negative 50. But my KEI, though, would be a positive 82 because the answer in part B is a positive 82 joules. So if I start at 6, my kinetic energy at 6 meters is already 82 joules. However, the net work done is negative 50. So if you think about it, negative 50 plus 82, right, will give you a difference of 32. But then to get rid of this 1/2, you need to multiply both sides by 1/2. So therefore, 32 times 2 is 64. So as you can see, you still have to square root 64, which will also give you an answer of 8. So in terms of doing part D, it's up to you where you want your references. I like going back to 0 because it's easy to add up all the areas without messing up on KEI. But that's entirely up to you. Okay? All right, I hope that helps. Stay ready. Don't be back.